Hello, everybody. Good afternoon to all participants of panel 6, Deep Decarbonization of Industry. I welcome you all to our session 2, named What to Learn from Scenarios and Pathways. So in the afternoon, again, we explore the interlinkages between industry transition and the energy transition by the means of several scenarios. So I'm looking forward to 4 very interesting presentations. And I'm also looking forward to all your questions. So please don't forget to post questions in the Woover tool. So we can put them to our presenters. So now we start with our first paper, which is presented by Sascha Samadi. It's a meta-analysis of industry sector transformation strategies in German, European, and global deep decarbonization scenarios. So Sascha, please, the floor is yours.
Yes, thank you, Stefan. I hope everyone can hear me. I'm happy to start off this session and present this work of ours. It was done by a colleague of mine, Klaus Bartel, and me, and it was financed by the project Sci for Climate, NRW. As Stefan said, we're doing a meta-analysis of industry sector transformation strategies, looking at German, European, and global deep decarbonization scenarios. Sorry, can you hear me now?
Yes, we can hear you again.
Okay, you can still hear me. Okay, sorry. We then did a meta-analysis of the respective roles of these key strategies in selected German, European, and global deep decarbonization scenarios. What we were trying to achieve by this was to identify similarities and differences in the available visions on how to achieve deep emission reductions in the industry sector. And we wanted to support the discussion on how deep emission reductions in the industry sector can be achieved and which strategies will be needed to be pursued, to what extent.
Sascha, I can't hear you. Is it only me?
For some reason, I'm being muted every now and then. Let's try again. Can you hear me now?
Yes, I can hear you.
Okay. So we categorized strategies. We used 4 different strategies, or 4 categories of these strategies. Energy efficiency is the first one. Fittingly, perhaps, this is the eceee after all. I don't need to tell everyone that energy efficiency can be a very important element in achieving emission reductions. Of course, it cannot bring us to deep decarbonization alone, but it can help to sort of reduce the burden of the other strategies. Then we have another category here in green. Those are the climate neutral energy carriers and feedstocks. Here we include 3 different strategies. First is direct electrification, so the direct use of electricity. Then the use of hydrogen or synthetic fuels. And finally also a biomass use. And each of these energy carriers, of course, can substitute fossil fuels and thereby reducing emissions. We also have carbon capture as a category, which includes carbon capture and storage and carbon capture and usage. At least in some instances, CCU can also lead to deep emission reductions, but not in every case. And then finally, we have another category of reductions in demand for primary materials. This can be brought about by material efficiency, that is, for example, reducing the losses of materials in production. Circular economy, that is increasing the share of recycled materials. Material substitution means using less CO2 intensive materials, and end-use demand reductions means that, of course, we can also reduce the need for goods and services, for example, reducing car ownership. And this, of course, reduces demand for primary materials and therefore CO2 emissions in production. We looked at these scenarios. These are from 7 different studies. We looked at 1 or 2 scenarios per study. We have 3 studies for Germany, 2 for Europe, and 2 for the world. And these scenarios, especially for Germany and Europe, all achieve very deep emission reductions in the entire energy system until 2050. All greenhouse gas emissions are reduced by 95 to 100% in these scenarios. Usually by a little less in the industry sector, but still more than 90% reductions in the industry sector by 2050. So these are quite ambitious scenarios compared to some others. And then we have 2 global scenarios, which are a little less ambitious, but also, at least what the data is concerned, of course, globally, it can be more difficult to reduce emissions compared to Germany and Europe because of increasing demand and increasing industrialization. So we also look at these studies as they are quite ambitious in regard to reducing emissions in the industry sector. And all these studies also include very detailed descriptions of the industry sector compared to some other system-wide studies. So that's why we chose these scenarios and studies. Regarding the IEA, unfortunately, the latest Energy Technology Perspectives 2020 was released a few weeks too late for us to include this in our analysis. So we had to use the one before, which was from 2017. This shows the role of climate neutral energy carriers in final energy demand of the analyzed scenarios. We can see that all these 3 strategies are used in most scenarios, but especially an increase in the share of electricity and in the share of hydrogen and synthetic fuels. Only some scenarios rely also heavily on a stronger use of biomass. If we only look at the German scenarios now, to not run over time here, there are some scenarios from the German environmental Umweltbundesamt, a German institution, and also 1 scenario from the DENA. These rely quite heavily on hydrogen and synthetic fuels with shares of around 50 to 60% in 2050. And they use hardly any biomass. And we also see another scenario from the DENA study, which explicitly looked at how direct electrification can contribute to emission reductions. So that's why we all have a share of almost 70% of electricity in the industry sector in this scenario. And then we also have another study from Germany from the Industry Federation, which foresees almost no increase in electricity and no use of hydrogen and synthetic fuels, but instead relies heavily on biomass and also on CCS, as we will see in the next slide. So this slide compares the scenarios in regard to the use of CCS and CCU. In the middle row, it's the share of CO2 that is stored in 2050 relative to the base year emissions of industry. And we see strong differences here in the scenarios. Sorry. We see some scenarios that rely heavily on CCS, which includes this scenario from the German industry. Almost 50% of base year emissions are stored in 2050. And also the two global scenarios foresee 40 to 50% emission storage. And then there are some scenarios that also rely quite a bit on CCU and achieve about 10% of base year emissions and use the CO2 again in different applications. Now on to the strategies to reduce demand for primary materials. I'm also only showing two scenarios here for illustrative purposes. We have one scenario again by this German institution, and it foresees that all strategies that we identified in this category, all of these are used to quite a strong extent. Material efficiency, for example, is used, and there's a stronger increase in material efficiency assumed than in the past, and among other things by reducing losses in manufacturing. And also consumers are assumed to buy high quality and more durable or repairable goods. Circular economy is assumed to get much stronger, a strong increase in recycling rates. For example, by 2050, 67% of steel production is sourced from recycled materials compared to 40% today. Also, material substitution is assumed. For example, use of timber is increased strongly in building constructions to substitute steel and concrete. And finally, also end-use demand reductions are assumed. So more sustainable lifestyles are assumed, especially in the sector of mobility. For example, strong use of car sharing and ride sharing, and smaller cars and fewer flights. Another scenario, a bit of a contrast, another German scenario assumes only circular economy measures, and also to a more moderate extent. For example, here 48% of steel products steel is recycled instead of 40% in 48% instead of 50%. 48% instead of 40% of steel production is from recycled materials in 2050 compared to a reference scenario. So there's a wide variety of approaches in regard to the assumptions on reducing demand for primary materials in all the scenarios we looked at. These are just two examples. And this figure or table summarizes the comparison of the scenarios in regard to the strategies we differentiated. You can only see 9 strategies here, and I discussed only these 9 because it was very difficult for us to differentiate the scenarios in regard to energy efficiency. There was not enough specific information to compare these. One general thing to take away is that, interestingly, all of these 9 strategies, while used in many of the scenarios, there's always at least one scenario that does not use this strategy strongly. So these are the ones with a red 0 in it. While, I'm sorry, I wanted to go back. Yeah. These 4 strategies do seem to be the ones that are used most heavily in all the scenarios. So that's direct electrification, the use of hydrogen or synfuels, CCS, and circular economy. But again, not even in all scenarios these strategies are used, but in most they seem to be very important, and the other ones are only selectively used in some of the scenarios. So to conclude some general findings, the analyzed scenarios pursue many different combinations of mitigation strategies, and that indicates that there are different pathways towards deep decarbonization of the industry sector. We also can conclude that there's no widespread consensus so far on the most likely or preferred combination of strategies. It can be interpreted to mean that there may be room for societies to choose not to pursue certain strategies if other strategies are pursued strongly. Or another way to interpret it is to say that if we pursued all strategies strongly, then this could constitute a more robust approach to reach ambitious climate mitigation targets in the industry sector. So obviously, we cannot expect every strategy to be as successful as some of these scenarios assume them to be. So if we used all these strategies, then that might be the most robust way to achieve zero or almost zero emissions by 2050. Another finding is that, not surprisingly, the main priorities of each study's client appear to be reflected in the scenario's choice of strategies. So we see that associations that are more closely linked to the environment or also environmental NGOs prefer strategies that reduce primary demand for primary materials, as there are many ecological side benefits from such an approach, while the German industry calls for more CCS and biomass, which allows them to use most of the assets they are currently using. So of course, these interests always are reflected in the scenarios. And finally, just some further research needs. We think there's, sorry, this reminds me that I should, we think it makes sense to analyze more closely different key subsectors of the industry, for example, steel, chemicals, or cement. This was more of an overview of the entire industry. The studies we included typically do not provide detailed assumptions on the individual industry sectors. So it might make sense to look at roadmaps or specific studies on these subsectors and understand more closely what these different strategies mean in the different subsectors. And finally, it certainly makes sense to analyze in more detail the specific challenges and opportunities of each strategy. Okay, with that I close, and thanks for your attention. Looking forward to any questions and the discussion.
Yes, thank you, Sascha, for the interesting presentation, and thank you also for having the watch yourself on the timing. I'm still waiting for questions in the chat, but in the meantime, I have one question. I mean, you analyzed a couple of different German scenarios, and from the European and international level, it was less wide. But can you do you see different patterns between global, European, and German levels in your results?
Yes, partly. I did not focus on these findings here because it was my impression that we did not look at enough scenarios, so to say, to really make robust claims on this. For example, in general, it seems like biomass, an increase in the use of biomass is more prevalent in the European and global scenarios, with this one exception of the BDI study for Germany, the study of the German of the German Industry Association. But with the exception of that, I think other scenarios, global and European scenarios, assume more biomass use, which it could be the case that in Germany it is generally thought that biomass availability is very limited compared to today, and in other parts of the world perhaps biomass still has more potential. Also, again, with the exception of the study by the industry, German industry, other scenarios from Europe and the world appear to use CCS to a stronger extent. This is probably due to objections in the German society towards CCS. I would assume that there are more scenarios in Germany that either try to avoid CCS completely or use it only for these emissions that are impossible to reduce by other means.
Mm-hmm. Okay, thank you. So room for more analysis. And now we close with that for the meta-analysis of industrial decarbonization scenarios and come to a concrete scenario from Germany. And now we have a presentation by Tobias Fleiter on deep decarbonization of the German industry via electricity or gas, a scenario-based comparison of two pathways. So I'm looking forward to the presentation by Tobias.
Thank you very much for the introduction. Before starting, I'd like to mention that this study is a result of the common work done together with Matthias Rehfeld, Marius Neuwirth, and Andrea Herbst. And yes, I think it continues well where Sascha has stopped his talk now. So we've learned, I think, in the last years that deep decarbonization of the industry sector is possible. 95% decarbonization is achieved in many scenarios using different technologies, and that is, I think, a great progress already to, let's say, some 10 years ago. On the other hand, I still don't want to be a policymaker at the moment, because we've also seen in Sascha's presentation that there are so many different pathways, and they need so many, and everybody's saying decisions need to be taken early, investments need to come soon to have impact until 2030, and etc. But the pathways are totally different. And it's very unclear which of these pathways and following infrastructural decisions, etc., shall be taken. So that's why we, in this study, have compared two alternatives. One is focusing on the electrification of the industry, and the other is more focusing on the use of green gas. And try to go on next slide. Yes, so in doing so, we have done a bottom-up simulation analysis using our forecast industry model, which we used in several studies and developed over the last 10 years. I don't want to go into detail here, just mention very briefly that one main advantage of this model is that we can capture the abatement mitigation options in a very broad scope. So we have energy and process efficiency, energy carrier and process switch, also recycling and circularity options, and also material efficiency and substitution for all the industry sectors. So we can we have a very broad industry scope, I would say. And so we have defined two scenarios. The scenarios are very similar in most aspects. For example, economic growth. There's a slow, continuous economic growth in the industry by about 1%. The physical production in the individual sectors is more or less constant, follows historic trends. No dramatic changes. And when it comes to mitigation options, we have a very ambitious progress in energy and material energy efficiency and process efficiency. So diffusion of best available technologies, but also quite a few selected innovative energy efficient technologies that are above technology readiness level 5. Are diffusing through the technology stock. We have ambitious improvements in recycling and circularity, and also material efficiency progress in the end-use sectors, resulting in lower production and demand for these energy-intensive materials. So all these assumptions are similar in both scenarios, and then the main difference is the choice of energy carrier and the process switch. So in one scenario, of course, we go more towards electricity. The scenario is called focus electricity, and we also include new processes above technology readiness level 5, so they need to be at least pilot and demonstration scale today. The scenario focus gas, on the other side, uses green gas, power to gas mostly. So we can now look more detailed at the scenario focus electricity and the assumptions, I would just like to pick a few to give you an impression what is included in that scenario. This table shows the mitigation options for each of the individual industry sectors, and then lists a few of the most important choices we have made. For example, the steel industry is using hydrogen-based direct reduced iron route and plasma steel. It also, at least as important, sees a strong switch to secondary steel, electric steel, which increases from 30 to 60%. So really huge jump in the circularity in the recycling rates for that sector, with a huge impact on emissions. We have reduction of material efficiency in all the important sectors. For example, the cement production goes down by 10%. We also have a decrease of the clinker share, so less clinker is used for the same amount of cement. For the cement fuel mix, we still use a lot biomass, but more important, switch to low carbon cement types to also reduce process emissions. All these are currently still under development. We assume that they will achieve high market shares until 2050. And for the steam generation in the paper industry and others, we are switching to assuming electric boilers, but also high temperature heat pumps were still appropriate with the temperature level. Also a bit biomass as today's level in the paper industry, and some district heating. So this is just to give you a brief idea of the scenario. Now, how is the scenario focus gas defined? Coming from the finalized scenario focus electricity, we include three main changes. The first one is that clean gas, so power to gas, is available for all the gas users via the gas grid. This is implemented in the model very simple by just decreasing the emission factor of the gas that comes from the gas grid over time. And second, in the electrification scenario, we needed very high support of financial support of electric process heating in order to see that early in the market. So this financial support, of course, is not included in the gas scenario. For example, for electric boilers, electric heat pumps, electric furnaces, this needed to be included in the electricity scenario. And third, we also see some process switch in the focus gas scenario, although in a bit different directions. So for steel, we also see direct reduced iron, but here using power to gas instead of hydrogen. The glass industry actually sees less of a change, so we don't have the switch to electric furnaces. Instead, the gas-fired furnaces are mainly remaining. And yes, the ethylene production is all the high-value chemicals, olefins, via the methanol to olefins route, as in the electrification scenario, but now based on power to gas and not on hydrogen. So these are the three main changes that lead us from the focus electricity to the focus gas scenario. And then let's have a look at some of the results. Here we see the greenhouse gas emissions in both scenarios towards 2050. Both scenarios assume achieve reduction of about 93% compared to 1990, so quite substantial and ambitious reduction. Actually, the remaining emissions in 2050 are more or less only process-related emissions, mainly from the cement and lime sector, but also from a few distributed smaller process-related sources. By 2030, this is also interesting, we have a reduction of about 55%, which is in line with the sectoral target of at least 51%. And yeah, no, it overachieves the target. The target is actually 49 to 51%, so it overachieves the sectoral target a little bit in 2030. And we see that there are more differences in 2040, and they mainly relate to the CO2 emissions of the remaining natural gas. In the focus electricity scenario, the natural gas in 2040 need to be phased out to a large extent already. And many plants are replaced by electric fired plants. And in the focus gas scenario, this is not yet the case, and the share of power to gas in the gas grid is still quite low. So gas still has high emissions in 2040 in that scenario. If we look at the energy mix, so here we see the final energy in the figure on the top, and on the bottom we see the feedstock of the industry sector. First of all, in both scenarios, we have a substantial reduction of final energy of 160 and 200 terawatt hours until 2050. This is driven by the energy efficiency progress, but also the material efficiency and the decrease in recycling. And then the scenarios in terms of supply mix, energy carrier mix, the scenarios, of course, strongly distinguished. We have on the one side, in the focus electricity scenario, a huge increase in the direct use of electricity, which accounts for about 60% of the final energy in 2050. And this is, the picture is then completed by a smaller use of biomass, hydrogen, district heating, and ambient heat. But the main energy carrier clearly is electricity, direct electricity use. In the focus gas scenario, it's mainly power to gas and electricity that share, that together are the both dominant energy carriers, and then we have a little biomass and district heating use. For feedstocks, it's in the focus electricity scenarios mainly hydrogen, and in the power to gas scenarios, in the gas scenarios, it's power to gas, and a little bit of hydrogen for ammonia.
Tobias, you have 3 minutes left.
Perfect. So I'll jump over the hydrogen demand then. And I want to say a few words about electricity demand. So we've heard already in many presentations that renewable electricity will be key in these decarbonization scenarios that do not use CCS. So we have in the focus electricity scenario an increase of about 120 terawatt hours for power to heat, so electric heating, plus additional 200 terawatt hours of hydrogen. And this actually assumes, no, it's not the amount of hydrogen, it's the electricity that would be used to generate hydrogen via electrolysis. So here we have then a total increase of 130% in the focus electricity scenario, and even more in the focus gas scenario with 260% increase of electricity demand, accounting also for the electricity that would be needed to produce power to gas, although it's, of course, can also be produced in other places of the world. And we see the pressure on the electricity system will be enormous if such a scenario is implemented. So to summarize, we have developed two scenarios, focus electricity and focus gas. Both are very ambitious in terms of energy, material efficiency, circularity, and new innovative processes. And still we see this huge increase in electricity. If we would have assumed more today's level of efficiency and production and circularity, the electricity demand would be substantially higher. The pathways both achieve 93% reduction. Going beyond 93% would really mean to allocate the remaining process emissions for which solutions are not yet really on the table. So it might need to talk about CCS. Hydrogen and power to gas are both critical in the respective scenarios. yes, the high increase of electricity demand I just mentioned, and then I think the next step would be to, for us definitely, is to also compare the cost of both pathways in a transparent way, but also dig a bit deeper into what is actually, what are the consequences of these two pathways. So in the focus gas scenario, there tends to be a higher potential electricity demand and also potentially higher cost on the supply side, on the energy supply side. And in the focus electricity scenario on the other side, there is potentially higher or deeper intervention needed at the industry and plant side in many sectors, but also not in all the sectors. So in this direction, I think further research is definitely a good next step. Yes, I'm looking forward to your questions. Thank you very much. And I would also like to thank a very good review for this paper. Thanks.
Okay. Thanks a lot, Tobias, for the presentation of these interesting scenarios. It seems like it's a bit an afternoon weak point in our audience, and all those presentations are so perfect. But I still have some questions. So you have an electricity and a gas scenario as opposites somehow. And I was wondering, we had in the session this morning a presentation on electrowinning. Electrolyzers for steel making. So did you also consider this technology maybe for your electricity scenario?
Yeah, we did not include it. Indeed, we could have. I think to our assessment that the technology readiness level is still a bit lower, and the general consensus to go for direct reduced iron is still a bit higher in the steel industry. So that's why we have picked the hydrogen-based DRI process. But yeah, of course, being more consequent on the electrification, that could also be case to include that. Yes, but we're looking really on the as we already included options that are not yet on the market in many cases. We want to also produce scenarios that are more as realistic as possible, as implementable as possible.
Okay, thank you. And another question, I mean, your scenario also had a couple of ranges and compared all your scenarios, both. Is it possible to also order them into the categories that Sascha provided?
Yeah. Actually, it's like the categories we also work with typically, and I think in the paper it's more structured along these categories, exactly.
Okay, here's now coming a question from Wouver. Strange that I couldn't see it there, but anyway, we have it. So the first question coming from the chat is, what drives technology stock turnover in your scenario? Costs or technical age?
I jumped a bit over these methods things. We have, and it's also a bit complicated. On the one side, we have for all the steam generation, etc., we have a stock model that calculates the total cost of ownership of technologies, and then the kind of most cost-effective option gets the highest market shares. For new processes like the steel DRI, so really fundamental process decisions. This is an exogenous assumption, so there we did not endogenously model this. So it's a bit diverse. The kind of the fuel choice in steam and also in some furnaces is endogenously modeled, and other parts are exogenously defined.
Okay. So I have two more questions now for you. The next question is also a very, very good one. I would also really share that. Have you looked at the respective costs of the two scenarios?
Yeah, that's exactly. I was actually hoping that I could. I was hoping a few months ago that I could present that already today, but it's still under work, and it will definitely be the next step. And also, I think extremely important that unfortunately, if you look at the literature, there's also not too much available about the cost. So the investment, the capex there's only a few sources for different technologies and sectors where everybody's very uncertain about. So and then it's often also unclear if this is a greenfield plant or if it's a modernization of a plant, and what is the refurbishment or kind of the modernization cycle in the sectors, etc. All this plays a role. So I think yes, a very good question, and we definitely need to produce more facts on the cost on the cost side. But also this a bit lacking literature made us quite difficult for us to already publish on something robust on the cost. So
okay,
we're working on that, but yeah.
So do you have a gut
only thing is
feeling
that we
from
see
your work?
high running cost in the power to gas case, because we switch from very cheap energy carriers to extremely expensive energy carriers. So from coal to power to gas, also from natural gas to power to gas. So this is we see is the investment plays really a minor role in the overall cost assessment. So the running costs are extremely high, and yeah. I mean, that's the first conclusion that we have.
Okay. Thanks a lot for this very important impression. And the last question fits neatly into that. So the question is, what would be the main advantage of the focus gas scenario relative to the focus electricity scenario? It seems to be very costly. You already mentioned OPEX. Higher flexibility is the question, or higher TRL? So what do you think?
Yeah, or less intervention on the industry side. Yeah, for example, the glass industry would already be. I mean, the industry could decarbonize using green gas, and would not need to change too much. So it also is a bit different in different industries. But as we have such a high natural gas consumption today, I think it's the main advantage that the industry sector could relatively easily decarbonize in many parts, not in all. And we should not underestimate this advantage, and not only look at the energy system cost, because these interventions at the industry level can be a huge challenge if, for example, there's not enough space to electrify, and if there's a high reluctance to use new electric furnace technology, etc. So I think that's the main advantage now.
Okay, but of course, then the OPEX has to be paid. So thanks a lot. I have also got one question for Sascha. So maybe if we are quick, we can try to squeeze it in here. So the question to Sascha is, some scenarios use CCU. Do you know more explicitly what type of CCU is used? How is the lifetime of the CCU products considered? Definitely an important issue. If it's methanol to fuels, lifetime is not very high. Sascha, do you have any information on that question?
Yes, there is a little bit of information in the studies. I just tried to look it up because I couldn't remember in detail. But I think, for example, the European scenarios, they foresee quite a bit of synthetic fuels productions. So that's an application where pretty quickly the CO2 ends up in the atmosphere, but it's also used to some extent for the production of plastics. And so in that case, it is conceivable that there's that the CO2 is continuously recycled. That's the information I now have for the European scenarios for the European Commission. But in all of these studies, if they use CCU, there's not a detailed explanation of exactly how much CO2 is used in what application, and where the CO2 ends up, or if it's kept in a cycle. So unfortunately, there's not a lot of information in the studies.
Okay, thank you. Yes, I think also when we go into these questions, we do not only need CO2 emissions and energy balances, but in the end, we need also carbon balances in our scenarios. And that's the perfect word for starting over to our next presentation by Florian Ausfelder. It's on chemical industry, and I think we will hear a lot in the range of CCU. The title is Greenhouse Gas Neutral Pathways for German Chemical Industry. Florian, please, the floor is yours.
Thank you very much, Stefan. I hope you can hear me well and can see it well. I'm very happy to. Perfect. I'm very happy to present our results that we concluded in our study Roadmap Chemie 2050, Roadmap Chemistry 2050, that we did together with FutureCamp, which is a consulting company, and the funding came from the German Chemical Industry Association. For those who don't know us, DECHEMA is a scientific, technical, non-for-profit organization with a goal to promote chemical engineering and biotechnology. And I had the Energy and Climate Division at DECHEMA. Well, I will start with the final results to make life easy. So you see different pathways here, a reference pathway, a technology pathway, and a greenhouse gas neutrality pathway. And you see colored bars, which partition the emissions in 3 different scopes. Scope 1, as generally understood, is everything that comes out directly of the chemical industry. Those can be process emissions, but also emissions from power and heat coupled plants, which are run by the chemical industry, and they usually run in order operated to produce heat and not electricity. Then you have scope 2, which in our case is external energy supply. That can be district heating, it can be electricity from the grid. And scope 3, and that's something new in the study, actually includes the carbon in the feedstock. So we assume that all this carbon eventually ends up as carbon dioxide in the atmosphere, and that is why it is included here. If we look at the different pathways, we have a reference pathway, which is essentially a business as usual. We assume the energy efficiency gain that we observe in the industry, and we assume changes that appear externally, especially in Germany. That would mean that the power system gets more and more decarbonized. The technology pathway looks at new technologies and makes a judgment when they are going to be introduced, and this judgment is based on the economics. And as you can see, it leads to some reduction larger than the reference pathway. The greenhouse gas neutrality pathway also looks at new technologies, but puts them into place as soon as they produce a greenhouse gas saving. The reason why we don't end up at minus 100% in this case is that there are smaller sources for greenhouse gases in the chemical industry that were not especially modeled in this study, and we included them for completeness. These are also, and I want to mention that because we just had the discussion before, not all greenhouse gases are CO2, and CCS measures are not useful against greenhouse gases which are not CO2. So there need to be other measures like compensation, or in this case, maybe catalytic destruction, whatever you might come up with. So if we look at CO2, we have to make sure that we got our systems boundaries ready, and this is displayed on this slide. If you look at the center part, which is below the base chemicals, that's where all the magic takes place. This is where about 60 to 70% of the energy demand in the chemical industry appears, and that is also where about the same amount, even a bit more, of the emissions appear. Essentially, nearly all process-based emissions come from the base chemicals. These base chemicals then get transformed into intermediates, which then produce specialty chemicals and a wide range of products, which, as I explained before, are still judged with a CO2 or a carbon content, which is then released as CO2 into the atmosphere. In order to close the overall balance, we had to make an assumption with respect to import and export. So they need to be carbon neutral. We need to export as much carbon as we import. Otherwise, we wouldn't have been able to close it. So that's a mathematical trick. Also, in case we end up using CO2 as a raw material, in terms of these system boundaries, it doesn't really matter where the CO2 comes from. It gets deducted at the beginning, it gets added at the end. In addition, as I said, all the energy and emissions, they appear below the base chemicals, or within the base chemicals range, or the value is actually created in the specialty chemicals. So that is one of the major issues for the different chemical companies. Some of them have more base chemicals, some of them have more specialty chemicals, and it's a different situation for each of them. This is the range of technologies we looked at. Similar to the previous speaker, we made a decision based on the TRL level, what technologies we consider to be relevant. We wanted technologies which at latest in 2050 actually could be bought off the shelf. And of course, this is kind of like an arbitrary judgment. What you may see or consider missing are all the methanol to olefins and methanol to aromatics pathways. We excluded them because it was the explicit wish of the industry to make as much use of existing assets as possible. And the assets don't exist for these pathways in Germany. This is how we judged a technology to come into play. It's a bit of a complicated graph, so let me guide you through it. You see 3 black lines. The solid black lines represents a specific cost of the conventional technology at a given moment in time with a non-depreciated plant. The dashed line represents the costs of this technology with a depreciated plant. And the dotted line represents the CO2 emissions caused by this technology over time. You see the rise in the black lines, which are mainly caused by the assumption that the CO2 prices are rising. And you see the fall in emissions, which is caused by mostly caused by the electricity, which gets more and more decarbonized. So the overall amount of CO2 emitted gets reduced. With respect to this conventional technology, in this case ammonia production, we compare our novel green technology, if you want to put it that way, which is displayed in red. You got the solid red line as before, the non-depreciated new plant with that technology. You got the dashed red line as before, the depreciated plant with the new technology, and you got the dotted line, which represents the CO2 emissions of this technology. And in this case, you would have a water electrolysis to produce hydrogen, you would have an air separation unit, and you would produce ammonia. One thing we assumed in the whole study was that we have continuous grid electricity. So, and in order to do that, we also have to be fair enough and assume that the electricity essentially consists of the then present mix of electricity, and therefore it only gets completely decarbonized in 2050 and has a contribution before that. You also see 4 vertical lines. The first vertical line, TR9, says this is a moment in time where we assume that this technology can be bought off the shelf on industrial scale compared to the conventional technology. So we're not talking about a demonstration plant. This is, you can go to one of the big plant manufacturers and say, I want to have this plant at the same production volume as my conventional plant. The next vertical line is, as you can see, where the 2 dotted lines meet. So that is the moment where the new technology actually produces the equal amount of emissions as the old technology, and beyond that it gets better. So it doesn't make much sense to introduce that technology before, because you don't get any CO2 savings, but you get them later on. So it's an important line to watch out, and it's the line we use to determine when a technology comes into play with respect to our greenhouse gas neutral pathway. The third red line is when you have lower specific costs for a new plant. So that would be if you had the decision, you have a green field and you have to decide which plant you want to build. You would choose one or the other. In this case, the specific cost at that moment of time would be the same. And the last line compared these specific costs of a new built plant with an existing old conventional technology. This is an important line because that is actually the situation we face in Europe. We have conventional plants in place. And I would like to quote a colleague from BASF to that moment. We have run our cracker for 70 years and we can run it another 70 years. The chemical industry, unlike the steel industry, does not have investment cycles that are forced by the plant breaking down. So we can do maintenance. It gets a bit more expensive every time, but we can continue to run our plants in general for quite a long time, and then they are quite profitable. We also did a study on the sensitivity of our parameters, and we varied them between our base value between 50 and 150%. And as you can see, the biggest influence, which is not really a surprise, comes from the electricity cost and the fossil fuel price. So of course, if methane or natural gas remains very low in price, you have a very hard time getting competitive with an electrolytic process. If the electricity costs are low, you stand a better chance, and therefore you can move the technology in time back and forth, depending on how you change the parameters. We also looked into plastics recycling. We have mechanical recycling already in place. We assumed a growth and a more efficient recycling for plastics in the mechanical part, and we also introduced chemical recycling, which is in our case pyrolysis or gasification of mixed waste streams to some extent, and they actually replace virgin chemical feedstock coming in. Some results, and this is maybe worthwhile mentioning. If we change the chemical industry to be based essentially on power to liquid basic materials, we are not getting more efficient. Quite the contrary, we're getting very inefficient. There's a huge increase in energy demand. It actually doubles in this pathway for the same amount of production as we have at the moment. But of course, this electricity at the end, at least in 2050, would be carbon-free, would be decarbonized. If we look at the greenhouse gas emissions, as you can see, they're coming down because you essentially replace your scope 3 emissions. So this is a feedstock by power to liquid using CO2. However, I would like to remind you that this is kind of a self-fulfilling prophecy. So we wanted to reach zero on the greenhouse gas emissions, we reach zero. So that is not necessarily something that will actually take place. So this is like a backcasting model. It fulfills its function, it reaches its goal. But what we have to learn is what happens in the beginning. So what would be assumptions for forecasting models are the results of the backcasting model. You can see that around 2040, when all these electrolysis-based processes come into play, we see a slump of the greenhouse gas emissions. And if you look at the cost structure, this is like the OPEX cost, if you want to put it that way. It's no surprise. You also see the electricity cost becoming dominant, which is to be expected. We assumed a very cheap electricity as continuous electricity for 40 euros per megawatt hour. But still, you have to cover essentially the energy demand of the chemical feedstock. So if you look again at the greenhouse gas emissions at the different pathways, I have only shown you the detailed results for the greenhouse gas neutral pathway. This is how they look like. All of them come down, and of course the greenhouse gas neutral pathway essentially reaches zero. So this looks very nice. This is what we want to have. It's a very optimistic picture. But now we come to the pessimistic part of it. If we look at cumulative emissions instead of the yearly ones, we see that even if we want to do and implement all the changes, for a long time, nothing much happens. And for a long time, we will essentially emit a lot of CO2 in the atmosphere that will remain until 2050. What I want to point out of it is we can wait for the perfect technology to be in place 2050, and maybe that will reduce to zero further emissions. In this graph, it would be a horizontal line. but it doesn't help us on the rise that we face right now. And we need to find pathways to decrease that rise significantly, not only in the chemical industry, if we really want to stand a chance against the emissions we put into the atmosphere as a whole, because at the end of the day, it's the cumulative emissions that count, and not if we reach zero emissions in 2050, when before that we didn't really care.
Okay.
And
Florian, are you coming to an end?
Yeah, I'm nearly done. Just the electricity demand. The electricity demand in the greenhouse gas neutral pathway of the chemical industry would reach the level of the overall electricity demand in Germany. So, and that would just be put in place for the chemical industry. And finally, within these different pathways, there's of course a change of feedstock composition. So the reference pathway stays like what we see at the moment, essentially fossil feedstock with a bit of biomass. The technology pathway is far more diverse. And finally, the greenhouse gas neutral pathways requires a lot of CO2 in order to produce the artificial feedstock that we need. I think that is the end. Just the people who were involved in the study, and thank you very much for your attention.
Okay, thanks a lot, Florian, for this comprehensive presentation. You also got a couple of questions, and I also have a number, so we have to be quick with answering, otherwise we will not have enough time. Maybe one remark on the efficiency. I guess that's because the feedstock today, the fossil one, also has lots of energy, which then has to be supplied, and that was what sounds like or looks like a less efficient system. However, you are probably right, like in other industries, efficiency doesn't really increase with decarbonization. But now let's go to the questions from the chat. The first one is, how realistic is the trade balance assumption when compared to today's balance, and what have to change to satisfy the assumption? So I think you assumed that trade balance remains stable, I guess.
Yes, the problem is there are no trade balances on the level of carbon contained. There are trade balances in the terms of value of product and overall overall volume as in mass, but there's no carbon content based balance. So we really don't know. This is an assumption that we took for obvious reasons, but we can't prove it at the moment.
Okay, yeah. Difficult issue. I think there can be much repercussions on imports, etc. And so the next one is a conclusion of your example figure on ammonia that the stock exchange must start much before it is economically and ecologically attractive. And I would also add on that question, I mean, isn't that a hint into policy that we need policies when we want to have that change earlier?
Yes and no, I'm not quite sure if it only comes down to policy. Yes, you're right. If we want to reach the greenhouse gas neutrality, we would need to start earlier before it is economically feasible. The question is, can you make it economically feasible? And one of the measures we already included was a CO2 price, but that is not sufficient to make that move.
Yeah, of course, it can be maybe other instruments, but there is also a question on the CO2 price, whether what cost development have you assumed, or have you assumed any?
We assumed a start of 25 euros per ton CO2 at the moment, and we reach 100 euros in 2050. That might seem a bit low, but I would like to remind everybody that the chemical industry, as well as other industries, have quite a few exclusions. So they don't really pay their full price at the moment. In our study, they would pay the full price on all the CO2 emissions they have, including the feedstock ones.
Okay, yes. There's another interesting question here in the chat. Many chemicals are feedstocks for the manufacturing sector. So what do you guess impact would be of a 50% cost increase of chemicals, base chemicals, to final consumer products? Do you have any ideas on that?
Well, we had a similar discussion this morning with the steel industry or the cement industry. So basically, the value happens in the specialty chemicals and not in the base chemicals. So if you would increase If the increase would be, let's say, 100% on the price on the base chemicals, you probably would see a 5 to 10% increase in the specialty chemicals at most.
Yeah.
So there might be a chance for a market pull if the following companies are willing to pay a little bit more in order to use these kind of chemicals.
Mm-hmm. So it wouldn't kill us in the whole economy, but it's very significant for the basic manufacturing. Then there is another question on the how do you justify the decrease in the production cost of the decarbonized ammonia plant from 31 to 2050 in the graph comparing the two technologies? Oh, that's very special. I recommend maybe you answer that afterwards. Maybe the one who posted, you can email it to Florian directly.
Well, it's actually, the quick thing is the decrease is due to the reduced cost of the electrolyzers. We assume that they get cheaper.
Okay, good. And the last one is on the investment cycles. Wants to have more explanation on that. Is it the same for all the sectors, essentially? I guess all the chemical industry sectors, because others are different.
Others are definitely different. The chemical industry has a huge variety of different processes, and some of them, especially those which are thermal processes, might be subject to similar rules as you see in the steel industry. But the big chemicals that we see don't really have an investment cycle as such. Mm-hmm. So we can just continue running the plants.
Okay, good. So thanks again for the presentation and all the insights. And now we have to quickly move to our last presentation today. And this is about cement industry, but different from most of the other presentations we had. It's not in Europe, it's from Africa. And so I'm very happy to have Maria here presenting an assessment of transition pathways for the Nigerian cement sector. Maria, please. The presentation is here, but not Maria.
Hello. Yes.
Hello, Maria. Yes, now we are hearing you, and I can see you. I guess the others don't. All fine. Please start.
Yeah, now I can't see my slides.
Okay, you have the title slide.
Oh, got it.
So now is the first slide, I would say.
Yes. Okay. So since I am not able to turn back, I will introduce myself on this slide. My name is Maria Yetano Roche, and I'm going to present an assessment of transition pathways for the Nigerian cement sector. This is a set of preliminary results. I hope to walk you through some interesting facts and show you our open questions, and maybe you can help me. So regarding now this first slide, Nigeria, apart from being Africa's largest economy, is also Africa's top clinker and cement producer. It is said to be on course to be the one among the top producers in the world. But here's one of the main in this preliminary study, because in fact there are very few projections and studies looking specifically at Nigeria from a more bottom-up perspective. There is one study which took place in 2017 and used Nigeria as an example of what could happen in West Africa, in sub-Saharan Africa, comparing different economies, and it's shown here. And it struck me as basically the only study that chose to put a spotlight in Nigeria as opposed to other emerging economies. And it has since not been followed up. So we took it from there. We noticed that there was reliance on projections coming from integrated models and rather global models. So the idea is to see whether we could say something more coming from the national data. Right, so it is indeed clear that cement production is going to increase strongly in Nigeria. Just looking at the demographics, Nigeria is set to be the world's third most populous country by 2050, and round about 2018, it became a mostly urban country. So there in the left-hand side panel is that cross signifies when urban population became more than the rural population. And the right-hand side panel also shows you that Nigeria, in red, has a faster urbanization rate than the rest of West Africa and then the rest of Africa. So that, compounded with an already large population, signifies some strong increase for the future. But what's not so clear is how the macroeconomic trends would drive consumption, production. There is, I found a global study, a mission possible, that was reviewed by Sascha as part of their study, giving a strong sign that in the emerging economies or the emerging cement producers, so South and Southeast Asia and Africa, it's GDP mostly that is going to be the driver, and increases in GDP per capita, but it's not yet clear how this link works exactly. So that's another open question for us, but we started looking at that from the perspective of what data is available. And finally, also there is very little on what are the decarbonization pathways related to those emerging economies. There is already a roadmap for India with a lot of information, but currently very few other national studies. So to get to the context of the let's say literature review and some stakeholder conversations that helped. In Nigeria, basically there is an oligopoly of 3 key players, the Dangote, Lafarge Africa, and BUA group. Dangote is a very important company. Some of you may have heard of Mr. Dangote. He is the richest person in Africa, one of the richest person in the world. And has, for example, the plant in the picture, that is the Obajana plant, is the largest cement plant in Africa with a capacity of 10 million tons. In total, Nigeria has currently 47.8, well, let's say 50 million tons of capacity. It has strong also Chinese investment within those companies. The capacity grew a lot over 15 years due to government policy. And now we have an overcapacity where the market is very geared towards taking on new demand and export. Another important characteristic is that it's relying more and more on coal rather than less. Nigeria is a major gas producing company, but there's a competition with the export market. The prices are volatile, the supply is erratic, so coal is an easier, less risky, it's a cheaper solution. And finally, the cement sector in Nigeria, like all the manufacturing sector in Nigeria, relies heavily on self-generation of electricity. They have their own generation plants. This, I think, is also important in terms of future technologies. Now, moving on to how we approached our very broad brush scenarios. We have taken 2 possible production trend drivers for our scenarios. One is based on mostly a growth in GDP and GDP per capita, together with an assumption on an increase of exports, and that would be the economic growth trend scenario. whereas another one is less strong, and it's just taking the same value of the urbanization rate, which is 3.75% per year. And it's also similar to what as that 2017 study assumed, although they had different starting assumptions. And then there are three pathways for the decarbonization assumptions, and very basically they are business as usual, moderate, and ambition. And the ambition one in particular has a more developed storyline where the investments are really realized to a high degree in terms of the plant modernization. Then these are the scenarios for production shown in the two graphs. One is the total production, one is per capita. The green line is the historical data which we obtained from the government, and itself obtained from the cement associations, Cement Manufacturers Association, but this is all there is in terms of information. And there you can see the strong increase. Then the blue line shows the urbanization rate production growth, whereas the red line follows a 5% growth rate, which is the stronger link with the economic growth and exports. Some market analysis that I've encountered project higher growth rates, like 6 to 8% per year for the next years, but my preliminary interviews saw that those were just too optimistic. And we have a range of assumptions taken from international literature, not yet from the manufacturers, relating to the main energy, main activity and intensity parameters. I won't go into the details of this, they're all in the paper, but we tried to find where possible African values, because Nigeria values were not published, and a lot was relying on the GCCA, Global Cement Association, which has its surveys. But I must say, the survey for Africa, the source itself mentions that it doesn't have a very wide coverage. So in general, we're working in a very data poor environment. And then just a word on the tool. I would not use the word model that I used to make a calculation based on those simple activity and intensity metrics, and also inspired by another tool that was developed by within that climate action tracker study. It does change depending on the data assumptions, but there is not yet, for example, explicit introduction of CCS or CCU within the parameters within the tool. Very preliminary results. I was pleased that the start year emission values, the estimate that I come up with is similar to those of other historical data. But as I say, there's very little to compare in terms of other forecasts. But let's say our set of assumptions come up to a net increase in emissions from the sector. There is no such deep decarbonization, I must say, mostly driven by the increase in demand and the very low penetration of decarbonization measures. In the strong demand growth scenario, there's a quadrupling of the current emission levels by 2040. It's the most difference made by decarbonization measures comes after 2030, and it has to do mostly with the clinker to cement ratio. And yeah, as I mentioned, there is still no strong assumptions on like use of CCS, mostly because there is no even remotely experimentation in Nigeria regarding CCS. Other studies, or the one study that has looked specifically at Nigeria, has much higher emission projections for 2040. It's around 100 to 200 million tons, and even in the ambition scenario. But I do think that their starting values are different, are not reliable. And just a few points. So we see a substantial emission growth even in an ambitious or in a decarbonisation scenario. We still need to work a little bit more. Maybe there's so much more potential out there. And I will explain our next steps. I do find some differences though with other studies in terms of the projections for production growth. In general, there's a lack of bottom-up scenario studies in key cement producers such as Nigeria. So that should be an important research recommendation. There is also the idea that there's a lot of climate finance currently looking for a target. And I think industry transitions in such major cement producers could have could be an important priority. So in our ambition scenario, we're putting a lot of assumptions on significant investments taking place, and I think a lot could come from climate finance. And finally, there's a lot of gaps ranging from the scenarios themselves to the base data, the export shares, which are not published for now, the energy efficiency potentials, and demand side measures, electricity mix, and thermal energy mix. For this, we are now beginning, after some pause in the funding, a collection of data from the experts and a dialogue with the stakeholders. And then I think there would be more developed scenarios that could then lead to some strategy decisions, or at least inclusion of the scenarios in Nigeria's review of its NDC later this year. And finally, the possibility of then making a deep dive to assess the techno-economic energy efficiency potentials. So, thank you for your attention. And once again, your thoughts and critical comments are most welcome at this stage.
Thank you, Maria, for these interesting insights into a quite different economy. And so there is already a first question in the chat. So this is, do you differentiate between the demand from infrastructure and from building construction?
No, I reviewed literature, and there is very little that one can put into a quantitative assumption. There is data on what is the need for infrastructure investment and for housing investment in Nigeria, but that doesn't mean that the need gets realized, and the idea of how much of that demand gets realized is the key data gap.
Mm-hmm. Okay, yes, probably very difficult for a country like Nigeria. I also have a question. You made these 3 technology scenarios, so to say, but I didn't really get the point. Which technologies did you assume? What is realistic? We had this morning a presentation from Heidelberg Cement, what they are planning all for decarbonization. Of course, they need not just CCS as well, but they have lots of technologies in their slides. What did you assume for Nigerian industry?
No, so I was going with the intensity values that aggregate different technologies. And that is just the first step. And then I hope to be able to understand what is the investments, what are the current technologies. There is information about that. But also what are the plans for new investments. But rather now there's very little experimentation with, say, fuel switching or there is rather a switch to more carbon intensive fuels?
Okay, thank you. Yes, this is probably very difficult, even more than in Europe. And so maybe to the audience, as this is more or less the end of the day, but if there are ideas or interests in this interesting research, you can approach Maria. And there is also the chat room after this session open, so it's possible to directly chat and discuss these interesting things. For me, I would say many thanks to all of you, to all presenters for these great presentations, to the audience for again a big number of great questions. And I hope to see you all tomorrow back in panel 6. We will start at 9:30 with a session on what initiatives and dynamics can achieve. So there we get more into industry perspectives, more into single industries like we have done with our last presentations today. And then we later have a session more focused on policy and again one on technology. So I hope you are interested in our panel and looking forward to meet you again tomorrow at 9:30. And one last advertising comment from my side. For all of you interested in the scientific papers, we are currently having an special issue open in applied science exactly on the topics of this panel. So if you are interested in publishing your work there, please approach me. I'm a guest editor there and can give you advice if you are interested to publish. Thanks a lot. Have a good afternoon, everybody, and enjoy the chat and the rest of the conference. Bye.
Thank you, Stefan. Bye-bye.
Thank you.
Bye.
Bye, and thanks, Rolf.